First International Physics Olympiad, year 1967, IPHO. Problem number 1. A small ball with mass big M equal 0.2 kg rests on a vertical column with a height h equal 5 meters. A bullet with a mass m small equal 0.01 kg moving with the velocity v0 equal 500 meters per second passes horizontally through the center of the ball. The ball reached the ground at distance s equal 20 meters. Where does the bullet reach the ground? What part of the kinetic energy of the bullet was converted into heat when the bullet passes through the ball? Neglect resistance of the air. Assume that g equal 10 meters per second square. Solution for problem number 1. Here we have momentum conservation in a horizontal direction. So it means that we can find what is the speed of our bullet and ball after collision. So first we can count what is total time to fall from height h. It will be t equal square root from 2h over g. And that would be time for both bullet and ball. So now we can find what is the speed of this ball after collision. That will be v2 equal s over t, which is 20 meters per second. Now we can find what is the speed of our bullet using momentum conservation. So we have mv0 equal mv1 plus big M v2, and from here v1 equal this expression, which is 100 meters per second. So now we can find what is the distance for bullet to travel. That will be v1 multiplied by time, which is 100 meters. That's the answer for the first question. Second question. We need to find what part of kinetic energy of our bullet went to the heat. This could be found from formula delta E equal E0 minus E1 plus E2. So we have these expressions for kinetic energies before and after collision. And from here we can find that total loss of energy was 92.8%. That was answer for second question, and here we solve problem number 1. First International Physics Olympiad, year 1967, IPHO. Problem number 2. Consider an infinite network consisting of resistors. Resistance for each of them is R, shown in a figure. Find the resultant resistance between points A and B. Solution. It's easy to remark that after removing the left part of the network shown in this figure with dotted square, then we receive a network that is identical with the initial network. It is a result of the fact that the network is infinite. So we can replace this network by this one, where big R is our resistance between points A and B. So for such a connection we have equation this one, which is quadratic to big R. That will be this one. And finally we have two roots for this equation, one of which is negative, which is not good, and the good solution is positive, this one. That was solution for problem number 2. First International Physics Olympiad, year 1967 IPHO. Problem number 3. Consider two identical homogeneous balls A and B with the same initial temperatures. One of them is at rest on a horizontal plane, while the second one hangs on a thread. The same quantities of heat have been supplied to both balls. All the final temperatures of the balls the same or not. Justify your answer. All kinds of heat losses are negligible. Solution for problem number 3. As regards the text of the problem, the sentence "the same quantities of heat have been supplied to both balls" is not too clear. We will follow intuitive understanding of this sentence, and it means we will assume that both systems, A, the hanging ball, and B, the ball resting on the plane, receive the same portion of the energy from outside. One should realize, however, that it is not the only possible interpretation. When the balls are warmed up, their mass centers are moving as the radii of the balls are changing. The mass center of the ball A goes down, while the mass center of the ball B goes up. It is shown on the next picture. Displacement of the mass center corresponds to a change of the potential energy of the ball in the gravitational field. In case of the ball A, the potential energy decreases. From the first principle of thermodynamics, it corresponds to additional heating of the ball. In case of the ball B, the potential energy increases. From the first principle of the thermodynamics, it corresponds to some losses of the heat provided. For the performing mechanical work necessary to raise the ball, the net result is that the final temperature of the ball B should be lower than the final temperature of the ball A. The above effect is very small. For example, one may find that for balls made of lead with a radius 10 centimeters and a portion of heat equal to 50 kilocalories, the difference of the final temperatures of the balls is order of 10 power negative 5 Kelvin. For spatial and time fluctuations, such small quantity particularly cannot be measured. Calculation of the difference of the final temperatures was not required for the participants. So that was a solution for problem number 3.